last time I've been doing some housekeeping. Change a few things. What was it? That math. Yeah, I added some function. I put the random values here and added sign, absolute, min, and max. Those are just basic functions. If A more than B, return B, and sine, cosine, and also RELU, all the way transfer function, RELU function. For if A is less than 0, is more than 0, return A. If A is otherwise, return A times an alpha value. That's not the standard RELU function. That's the leaky RELU. I think there's really no point having a difference between RELU and leaky RELU, so I just put them both together. The alpha value is 0.01, but it could be anything. And what else? Okay, sigmoid. I just copied it. I just copied the whole thing from our website here, and 1 minus 1 exponent on negative a. That's just sigmoid function, and then the derivative of sigmoid function is sigmoid function times that's 1 minus sigmoid function. Oh, actually 1 minus a. Oh, I made a mistake here somewhere. Oh, I just checked it out. It's not 1 minus a, it's 1 minus sigmoid a. Oh, what am I doing? It's 1 minus sigmoid a. Sigmoid a times 1 minus sigmoid a. Okay, so wrong, very wrong. Okay, sigmoid a times 1 minus sigmoid a, tan h. Is 1 minus tan h squared. Okay, the derivative of tan h. So all the derivative functions are here, so we don't have to worry about anything else. Okay, now let's do some other things. What are we? Pooling. Okay, now we need to do convolution. And there's really something a bit complicated about convolution. Is that here we have the matrix function, the fully connected feed-forward function. But the convolution function is basically the same thing as that, with some slight differences. Let's copy that, convolution forward. Convolution forward. But we're gonna have to make some slight modifications here. Okay, so I just take the scaling function and then just copy it because it's basically the same thing. But with, again, some very important differences. Are we here? Okay, matrix forward, no, convolution forward. This is the kernel function, convolution, let's just call it convolution. Index map convolution 2D. Convolution 2D. Okay, now I'm gonna have to figure out how to do this correctly. Okay, we just take the convolution value, and for each one, there's some details that are very, very different. Okay, we need a filter. Okay, we need a filter. Okay, index width, index height, result width, result height, and now we need filter width, filter height. Well, my filter width, filter width, filter index, filter length, not filter length, not filter width, filter length. Same thing as always. A few details. Now we're going to be copying everything from type image. Okay, what do we do here? For each pixel, for I, we need a sum counter. Do we even count it for index map? And then we follow the index, and then we add convolution and a source index times filter.j. Okay, let's see what do we change here? Okay, source index. Okay, sub equals source index times filter. No, oh, we have to add filter. Source image filter. Okay, filter dot. Can it be filter.j? Because there are multiple filters here. because the filter array is very large. It's filter index. We need filter index. Filter index plus j. So far, so good. Except there's no division. Okay, one difference with image convolution is that in the convolution operation, you don't use division. Okay, filter index is slightly more complicated, but everything else is basically the same, except you don't use division. Okay, so we don't need counter. We don't need counter here. That's for the forward value. Okay, so far, it's good. Filter index. But of course, it's not that simple. Okay, so we're doing a single convolution for a single index map, for a single value, because the number of filters is the number, is the depth of the source array times the depth of the result array. So there's a lot more. If there are 10, it gets really complicated, like really complicated. So I'm gonna have to figure out how to make them work one by one, because we can't do them all at once, and we have to sum up the results. Okay, I got it. So we're gonna have to do another really complicated thing. So we can't just use index map convolution. We have to use index map add. So you have to do each one separately, because there's a lot of filters. Like 10, if there are 10 images and 10 results, that's 100 different filters. So you have to do this 100 times, and that's if we have 10 by 10. It could be even more than 10 by 300 by 300, and we have to do this each time for each one. Okay, so source filter static. We have to do something else here. Index map add value. Index map, no, not index array, and kernel array index map convolution add. Not add, convolution value, because we need to add them together, but that's really complicated. Okay, so what do I need? We need filter, source, everything here, minus a few things. Okay, this is going to get really tedious real fast. I don't think we need result, because we just need the sum value. Okay, could our neural unit. Trying to think of how this is done. Not CUDA neural unit. That's something else. Type neural unit, and it returns a value here. It returns a sum, because we're doing pixel by pixel. So it's really complicated here. Index width, index map, result. We don't need result. Do we need result? Result index. Okay, it's gonna get really complicated real quick. Now I'm trying to think of what I'm doing, because we have to combine multiple filters into one. So this part right here is supposed to do one single pixel at a time and then add them together, because we can't do the convolution operation separately. This is really complicated here. Okay, I think I'm getting ahead of myself here. Before we do all this, we have to go through all of the pixels of the result length. Okay, that's matrix forward. We have to go through all the pixel of each, instead of individual pixels, we need to do all the filters on all the sources. So result array length. So this part right here, that's the convolution forward. Okay, so you have to sum up all the we need to replace this operation here with a convolution operation, and that's the complicated part. And that's the part I can't figure out. Okay, let's skip everything. Let's go to everything step by step. Okay, result source weights. Instead of weights, let's call it filters. Not weights, filters. Let's just go to everything step by step. Filter. Result source filter. Okay, if filter dot array depth, not array length, array depth, not equals, not filter dot array shape dot shape depth, not equals result. Now we need to rename this. Result dot array shape. Just copy everything. Array depth. Okay, the total number of filters must equals the depth of the source. What am I doing? Source dot array shape dot array depth. Is it source? No, not source. Pointer. Source pointer dot array shape dot array depth. Okay, that's the first part. The second part, for each item in the source dot array shape dot array depth, result dot array shape dot array depth, for each slice in the result array, we have to go. I forget that. We have to go to each item for each pixel. We have to go to each pixel in the. We have to go to each pixel in what else? Pixel in what? We now have to go to each pixel in the source in that particular slice. For I equals result dot array shape dot array something. We have to go to each pixel in the image. So we need to know the image size. Okay, let's get rid of that. Unsigned long. Okay, result. What is it? Result length. Result length. Okay, result count. Unsigned long, result length, and result count. Count is the depth. The length is the size of the two-dimensional slice. Count is the number of slices. Same thing for slice. Same thing for source. Result. Source. Okay, this is going to take a long time to figure out. Result, source, and filter. Okay, we need to go to each individual pixel. Okay, so now let's set those values. Count. Let's set them up here. Okay, well, get rid of this. Result length equals result.array shape.array width result.array shape.array width times result.array shape.array height. Now it's width and height. Okay, so far so good. Result.array depth. Result.array shape.array depth. Result count. Okay, so we just copy this and use it for all of them. Oh shoot. It shouldn't be too bad. Oh, it actually is too bad. What are we doing? Redo. Okay, copy this. Copy that. No, let's copy this. You have to copy it twice. Okay, copy this. Copy here and copy here. Okay, result. Source. Source. And source. Okay, stop doing that. Source. Source. Copy. Paste. Filter. Copy. Paste. Paste. And paste. Get rid of that. Get rid of that. Okay. If filter count not equals result count times source count return 0. All right. For I equals result depth, result count, we have, no, for j equals result count. For I equals result length. Result length, no, result length, not length. Result length. Okay, we need to go to each pixel. Okay, now get rid of that. Now we have to go to each pixel in this thing right here. For equal result length. Okay, index width. Oh, we have to make sure that index width, if index count, no, not index. What am I doing? What is index? Oh, we forgot to include index. Oh, that's stupid. Oh, what am I doing? Input. Everything's wrong here. Index map. Okay, are we in the right place? Yeah, filter index map. Okay, if index map not dot index width not equals result length, or index map dot index height not equal. Okay, we're getting close. Not equals filter. Is it filter count? No, filter length. No, filter length. Okay, filter length. Then return 0. Okay, the size of the filter has to equals the height of the index, because that's how we know everything is. Result length. For I equal result length, we have to go to each pixel. Now you copy this part right here. For each pixel in the index height. Okay. Okay, where am I? Okay, for each pixel. Oh, is it IJK? I'm losing counters here. We need to put it in a separate function, because otherwise we're gonna get seriously lost. Okay, for each pixel, we need the convolution value. Index map add. I'm gonna have to really change everything here. Okay, we need to get the individual pixel. Okay, how do we do this? Okay, now is the time we do the other thing. Filter result source length. For now, in here we go to each pixel in the result, but here we have to go to each pixel in the source. Where are we? Source length. We have to go to each pixel in the source. Okay. Now we go to each pixel in the index again. Each pixel in the index, and then do the thing here. For each pixel in the length, to the forward, we have to go for each pixel in the source count. We go in each pixel in the length. But there's something else we have to add. Now we have to result index result length equals the size of the slice. But now we also need result count, not result index, result count, because we need to know the number of counts of slices. Result count, source count. The problem is that we have to do several operations in all at once. We need to go to each of the source slices. Then we have to go to each of the indices, and then we have to go to each of the results. Not in that order, but we have to do all three of these things at the same time. That's why it's so complicated. Filter length. Why am I filter length? Filter count. Okay, index is where we start. For I equal filter source count, not source length, source count. Count. Okay. Okay, do I have source count? Yeah, we have source count. So why is it complaining? Less than source count. Why is it complaining? Undefined? It's right here. Oh no, source index, source length, source count. Result, source count. Why is it complaining? I have no idea. Okay, for equals source count, we have to copy everything here into yet another function because now we have to do it pixel by pixel. Oh, this is really getting complicated. Okay, where are we? Okay. Okay, now we have to do everything pixel by pixel. Okay, for, let's copy it here. Sum equals 0, k equals something else. And, okay, I'm getting ahead of myself here. Okay, for each pixel in the filter, index height, for each pixel in index height, that's the size of the filter. We need to add, we need to find the index. We need to get the index, and then we do same thing, and then we add the source times the filter. But now we need the filter index times index. Okay, j. Okay, j equals what? Result offset. Okay, I'm confusing myself here. The point is you have to do at least 6 or 9 different operations all at once, and they all have to be nested inside each other. Okay, just to be clear, let's just do it straight, because if I have to do everything in separate functions all at once, it's just gonna confuse me all to hell. So let's just go straight and see how far we get. J. This thing is ridiculously complicated. For each pixel, for each pixel, we need to go to, let's call it in order. K. For K equals source length equals not result length. For K, why am I? So K equals source length, source count. Source count. Now you're gonna see how complicated this thing is. Source count. Okay, now we have source count. What else? For L, yeah, this thing gets ridiculously real quick. For L equals IJKL. Wait a minute, L. We're just gonna go straight and then we'll optimize later. For L equals filter index. Okay, after a long time, like several hours, I finally figured out how to do this right here. Okay, this is for getting the convolution operation for a single pixel. Remember, if we have 10 source images in the source and then 10 images in the result, that means 100 filters. So we have to do this each time for each filter, 100 times. But it's worse than that because we have to do it for each individual pixel because we have to sum them up. Because we can't just do it directly. Okay, so what we're doing here is this operation right here. This is for the fully connected layer, but we need to convert this multiplication right here into a convolution operation. And this was what makes it so difficult. Okay, here, we're doing this for one individual pixel. It just returns the sum of a single convolution operation. Okay, to do this, we need to know which filter we're using. That's the index offset. Index offset is which single pixel in the result, in the result filter, because we have to do it for each individual image and then for each individual pixel. Okay, index offset tells us which individual pixel in that particular image. And if there's 10 images, that's 10 times the number of pixels. Okay, here the index map is a column. Is a row of columns. So the J here represents the first item in the particular column we are using. Remember, we are doing it one column at a time. So this tells us index offset tells us which column that we are using it on. And then for I, we're going for each item in the column. We're going down, and then J plus index width right here. That's we're going down each item in that particular column. Okay, first we take the index at the location of the index map, make sure it's valid, and then we multiply the source by the filter location. Source index equals the particular image in the source array, the particular image in the source array that we are using, and filter index is the particular filter in the filter array. Okay, the filter array is a concatenation of multiple filters, so we need to know which one that we are using here. And then the I is index I, which particular pixel inside that particular filter. So there's a lot of things being stacked on top of each other here. That's why it takes so long. Okay, so the particular image in the source, and then the particular pixel in that particular image multiply together. This is one single convolution operation. This is one single convolution operation, and oh wait, no, that's right. It returns the sum, the result of that particular convolution operation. All of this for one single convolution, and then each image has multiple pixels, so we have to do this for each individual pixel of every single image. Okay, now we have to make this work. Okay. Oh, let's copy. We need to copy all of this here. For I equals result of array length, for J equals result of array length. But there's another part we have to copy here. Okay, for J equal result length. Result length or result count? No, result count. Because we're not going pixel by pixel, we're using slide image by image. Result count. We're going image by image. For J equals result count, sum equals 0. And then for K, for K I'm going to use something else. For K, because we have to go to each pixel in the result array, and then for that particular pixel, go to each image. For that particular pixel, go to each image in the source array. So you have to do it out of order here. For K equals 0. This is really complicated. Oh my god. Okay, K less than result length. We have to go to each individual pixel in each individual image. Yeah, for each image, for each slice, go to each individual pixel, K++. I'm trying to keep everything relatively similar. Okay. And now we copy this inside this. And hopefully, let's just advance format document. Okay. Now let's see if we can get this to work. For each image in the source count. Okay. In the source count, now we need to replace this with a convolution operation. Okay, which is right here. Let's just copy it and then try to get it to work. This is really gonna take a while. It's really complicated here. Okay, static sum equals 0, sum plus equals context map individual in convolution. Go source.array data. Source.array data no, just array data. We don't need that. Filter.array data. Array data, index width, index map. We already did that. Just copy all this. Where are we? We already did that. Index map here. Okay, index offset. Okay, so each that the particular pixel, yeah, it's k. Okay, it's definitely k. Index offset is the particular pixel in the result for I equal result length. In that particular result, you have to go to each individual pixel. Oh, that is tedious. Okay, source index. What is source index? Is source length. Source. We did this before. It's the same as I think we did it. Yeah, it's the same as the one here. Parent length times I. It's the same as for the index map pooling and scaling. So this shouldn't be too difficult. Source length times what? Times I. Yeah, that's the particular image in the source, I think. Source index, the particular image. Source length is just source length by itself. Okay, filter index. Okay, this is complicated. Filter index equals filter length. We need to the specific index, the specific filter, or in the filter array. Filter length times which filter are we using? I equals source count. Filter length times I times not I. Filter length times I equals J. No, it's J. It's J because it's a two-dimensional slice. Is J times source count. We need to convert the filter array into a two-dimensional array of filters, not a array of pixels, but an array of filters. So let's think of it like an image. J is the y value, is usually the y value, which is the length of the source count times source count. Yeah, that's it. Source count plus I. Okay. Okay, think of it like a two-dimensional image. We need to each filter represent one pixel. Okay, just like doing image, and then filter length is just filter length. Okay, no, it's the same thing. We already did that. Okay, filter length. This is really hard to keep track of, but it does work. We need to know the actual filter index, which is like an image in a two-dimensional slice, and then result.array data dot it can be J. Okay, J in the specific J times result the specific pixel in a particular image. J is the result count times result length plus K. Okay, so I think we got it. I have no idea if this is right, but visually it looks right. Okay, so it looks right. Okay, so we're getting for each pixel in the result, go to each image in the source, and then for that image, for that image in that particular pixel, get the sum of all the images in the source times that particular array of filters. We remember we have 10 by 10. If we have 10 by 10 images, we have 100 filters. So we need 10 of the filters. We need to know which one we're getting. And since a two-dimensional image, that gives us that particular it's a row of column. It's a row of filters. We need the particular filter in that row. Okay, that looks right. Convolution forward. Now let's do convolution reverse. Okay, one more thing. It's not just convolution reverse. It's convolution 2D reverse. We have to be very clear about this because otherwise we're getting things wrong. If we try to do 3D convolution, something's gonna go very wrong. 2D reverse. Okay, make sure everything is exactly the same, except that instead of source, we're doing result. Okay, everything else. Okay, right here, just like matrix reverse, we change everything. We just reverse everything. Okay, instead of J, we use I. For I equals source count, and for I equal result count. And then for the K, we do for K equals source thing. Okay, I'm gonna have to think through this because some part of it is not quite clear. We do everything exactly the same, except that we're going to source. We're going to the source instead of the result. For k equals source length, are we doing source filter or result filter? No, we need result array. Okay, result. Return everything result length. Remember that the result length is not the same as the source length. The images have to be the same size. Do they? Oh no, they don't. Source result length equals source count. No, this is the same. This is still the same because the shape of everything is still exactly the same. We're just getting different values here. Okay. Is it still k? Source length. Yeah, everything's the same. We're just reversing the source and the result. Source dot result length equals source length plus k. Remember, everything is still the same. No, it's not. It's not j. It's I. No, is it I? I don't think it's I. J. No, I think it's I. I times source length plus k. Yeah, it's I. Yeah, it's I times source length plus k. Okay, we're doing an image. I times source length plus k. Source count. Is it source count or yeah? Is it? Yeah, it is. Now I have to make sure I didn't mess up anything. Okay, even with all this, we're not even sure that we got everything right because we won't know until we do the convolution for real. Now I need to figure out a way to test this to make sure I didn't mess up anything. Okay, so it should be right. Well, if it's wrong, we make corrections later, but so far it was good. And of course, we made a mistake. It goes here. This right here goes here. It goes inside because we are going to each pixel and then summing it up. So the pixel should be inside the loop, not outside of it. Oh, that's a stupid mistake. Okay, so the pixel should be inside the loop right here. For result count, result length, sum equals 0, and then we go to each and we find the result of sum and then set it. Ah, this is the part I forgot. And k wouldn't have any meaning if it was outside. Oh, that's a really stupid mistake. Okay, I'm just searching for mistakes here. It has to be inside the loop. Set everything up. And we're good. Okay, we'll just keep hunting for mistakes. And there are probably a lot of them. Okay, get rid of a few things. What else? Am I missing anything here? Get rid of that. Okay, next thing is add the convolution layer. Okay, file, new, file. Add a file. Okay, what do we copy from? Convolution bias. No, not bias. Pooling. Yeah, scaling. Scaling should be right. Okay, convolution. I need to know what we need here. Convolution layer, pragma once. Okay. Scaling convolution. Convolution. Layer, no, layer, convolution. Why am I keeping typing it? Copy it. We don't need to do this tonight because it's just gonna take a long time. Let us do it anyway. Convolution create. Okay, we do need to know the source height here, just like with scaling. Convolution create is type layer create, type new layer convolution. Convolution. It's getting a bit late. I don't even know if I can do this tonight, because we have to create everything in a particular order. I don't feel like doing that tonight. I'm gonna do that tomorrow. Let's do that for now.